In this lecture, we'll start by looking at plate theory, which is really just an introduction to rate theory, which includes the Van Deemter equation and is a wonderful mathematical treatment of all of chromatography that we can use to understand multiple types of separations. If we want to start with plate theory, then we'll need to start with a column that we can divide into a number of plates. These are theoretical plates, which are all mathematically equivalent. How many plates? We'll need n of them. This is the number of theoretical plates. And each one of these plates is going to have a plate height of h. And the way that we can find that is simply relating the length of the column and the number of theoretical plates. So as we go down this column, we'll establish an equilibrium at each stage between the mobile phase and the stationary phase, and then we'll transfer the mobile phase over to the next plate. Now, assuming incompressible flow, we can do all the math out to make this make perfect sense. But plate theory fails to account for band broadening in a mechanistic way. Basically, it neglects solute, diffusion, flow paths, etc. Rate theory, on the other hand, does account for these things. It was created by J.J. Van Deemter in 1956 and is the topic of the textbook, chapter 26, starting in section C. And it accounts for things that plate theory neglects. It can predict the effect on performance of things like phase properties, solute diffusivities, partition coefficients, phase velocity, flow rates, support size and porosity, etc., etc. Now, rate theory took a look at the equation or the empirical relationship that related the linear flow velocity to plate height that we can calculate from the equation for the number of theoretical plates that we can derive from a chromatogram that was associated with the plate theory that we just talked about, and the relationship between the plate height, the length of the column, and the number of theoretical plates. Surprisingly, what we see when we vary the flow velocity and calculate the plate height, empirically, we find a curve that looks kind of like this. And if you examine this curve, you can pick out a couple of different components. There is a component like this, there's a component like this, and then there's a elevation component. And that simply displaces the entire curve up from the baseline. So let's see if we can go through each of these components, give them a name, and see what physical parameters give rise to these different terms in a final equation. This equation is called the Van Deemter equation, and by going through this in detail, we can really learn a lot about how to optimize a separation.